Welcome to section 13.2. In this section, we are going to continue looking at vector functions and vector equations and how we can apply a little bit of calculus to these topics. So we're going to talk about some derivatives and integrals. So to start off, we have the derivative of a vector function. So we have dr dt. So notice the bolded r there. We have r prime of t. This is a vector function in terms of a parameter t, and we're taking its derivative. The definition and the derivation for derivatives of vector functions are very similar to our definition for scalar functions, like back in Calc 1 and Calc 2. So we have this formula, the limit as h approaches 0, of r of t plus h minus r of t all over h. This is the difference quotient, so it's just a kind of converted version of the difference quotient that now applies to vector functions. And we have t as the parameter instead of using x as like the variable. So r prime of t is called the tangent vector. So we have the tangent vector. We will find, as we're going through more topics on vector functions and derivatives, that we may need what we call the unit tangent vector. To get the unit tangent vector, we need to take the tangent vector, so r prime, and then divide it by its own length. That's what gives it a length of 1 and makes it a unit vector. So the notation we use is capital T of t. Okay, so capital T representing unit tangent vector, little t is still the parameter, equals r prime of t over the magnitude of r prime of t. So it's the same direction as this vector, but now it's been divided by its own length, so the length of this vector is 1. Now when it comes to differentiating vector functions, so we have this 3-component vector f of t, g of t, h of t. It turns out we can derive using limits also that the derivative works exactly the way we would want it to work for these vector functions. So r prime of t is simply going to be f prime of t, g prime of t, and h prime of t. So we're able to just essentially distribute the derivative into every component of the vector. So there's no like special tricks or rules we have to learn. We can just take the derivative one component at a time, and that results in r prime of t. So for example, find the derivative of this vector function. So this is in our standard basis vector form, so ijk form here. So we can go ahead and just go component by component, taking derivatives with respect to t. T is our variable. So up here, we're going to get 3t squared I. Next, we get t times e to the negative t. This is a product, so we are going to be encountering the product rule here. So like first times derivative of the second, plus second times derivative of the first. So that would be negative t e to the negative t plus e to the negative t, or vice versa. And that's the j component. Plus derivative of sine is cosine, and this is a 2t, so we have to employ the chain rule. So that's going to get multiplied by 2. And then that's our k right there. So this is the derivative. Okay, so this is the tangent vector. Then for part B, we want to find the unit tangent vector at the point where t is 0. Now, if we were not given this part, if we just said find the unit tangent vector, we could come up with the formula for the unit tangent vector because we already know r prime and we know the formula to find the length of r prime. So we could create a very extended formula in terms of t. However, because we only care about the unit tangent vector at the point where t is 0, we can go ahead and substitute in 0 first, and then just take the length of that with all numbers instead of working with the parameter t. So we're going to go ahead and take r prime of 0. So that's going to be 0i, that's 0 and 1, so just 1j. And then plus cosine of 0 is 1, and then times 2, so that's plus 2k. So that is the tangent vector at t equals 0. So the unit tangent vector is going to be, so that's j plus 2k over the length of this vector. So we take the square root of the sum of the squares of the components. So that's 0 squared for the I, plus 1 squared for the j, plus 2 squared for the k. And that is going to be radical 5. So we'll go ahead and move that in with each expression. So 1 over rad 5j plus 2 over rad 5k. And that would be our unit tangent vector. So same direction when t equals 0 as r prime of 0. But this one has a length of 1, whereas the other one had a length of radical 5. We have lots of properties of differentiable vector functions that we can look at. A lot of them are very similar to what you would have seen for scalar functions back in Calc 1. So we've got derivative of u plus v equals u prime plus v prime. So you can split derivatives across vector addition. Derivative of c times u equals c times u prime. So you can pull constants out of derivatives. If we have f of t times u of t, so this is where f of t is a scalar function and u of t is a vector function. Because if we're multiplying vectors together, then it would have to be what these two are, either a dot product or a cross product. So we have a scalar function times a vector function, and we employ this kind of similar version of the product rule, where we have the derivative of the first times the second plus the derivative of the second times the first. And then derivative of u dot v is going to be essentially the same formula, but with dots instead of times. And then u cross v, we're going to get, again, same formula, but with cross products instead of dot products instead of multiplication. And if we have a function u of f of t, so we have a scalar function inside of the vector function, then we employ the chain rule. So we take the derivative of the outside function times the derivative of the inside function. Okay, so all of these rules should look just like the ones you remember from Calc 1, but of course with our vector spin on them a little bit. So we're going to take a look at actually proving a property right now involving derivatives of vector functions. We will be referring back to this property in one of the upcoming sections, so we can actually see kind of how it gets used in other scenarios. So we want to show that if the length of a vector function r of t is c, which is a constant, then r prime of t is orthogonal to r of t for all t. Okay, so again, if the length of the vector is constant, then the derivative is orthogonal to the original. Now, if you're thinking like, well, but the derivative is always constant, it's always a number. Not necessarily. You could have the, or excuse me, did I say derivative? I meant length. You say the length is always constant. It's always a number. Well, not necessarily. You could have a formula in terms of t, but if we don't pick a specific value of t, then there's still going to be a variable in that formula. So it's not guaranteed that the length of a vector will be a constant unless you plug in a specific value. But what we're assuming here is assume that this is true. So assume that its length is constant for all values of t, and prove that r prime is orthogonal to r. All right, so first thing I want to take a look at, we know, or I should say, we assume length of r of t is equal to c. If we go ahead and square both sides of this, this is still equivalent. This is still equal. And this expression on this side, the length of the vector squared, that relates back to a dot product property that we had talked about in a previous section. And that is that if you take a vector and dot it with itself, you get the length of the vector squared. So this side actually can change into r of t dotted with r of t. And the right side will remain c squared. So we're going to take this and use this as kind of our starting point for our proof here. So we're going to go ahead and differentiate both sides. So I'm going to differentiate. And just as a note, I'm also going to switch the sides because I want this one to be on the left. So, and switch sides. So I'm going to take the derivative of c squared. C is a constant, so its derivative will be 0. And then we have derivative with respect to t of r of t dotted with r of t. Okay, so again, the c squared is a constant, so its derivative is 0. And then we have the derivative of r dotted with r. So if we go ahead and employ property 4 from up here, we're going to get, this is r prime of t dotted with r of t plus r of t dotted with r prime of t. And now if we recall another property of the dot product, the order does not matter. A dot B is the same thing as B dot A. So we can switch the order of either of these and it will still be equivalent. It will still be equal. So we can switch these two around. So we get r prime dot r plus r prime dot r. So we actually have 2 of those of r prime dot r. So if we look at what we have at this point, we have 0 equals 2 times r prime dot r. At this point, we can divide the 2 away, and because when you divide it under the 0, it just goes away entirely. So all we have left on this side, we're going to have r prime of t dotted with r of t, and then we have a 0. And if you recall, one of our major properties of the dot product is that any 2 vectors, if they are dotted together and get 0, those vectors are orthogonal. This is how we test for orthogonality. So since the dot product of r prime and r is 0, they must be orthogonal, which is exactly what we were trying to prove. So we can say, thus, R prime of t is orthogonal to R of t. And we can go ahead and just put a little box there to signify that the proof has been completed. So if we have a vector function of t whose length is constant for all values of t, then the derivative of that vector function will be orthogonal to the original. So let's take a quick look now at integrals. So we looked at limits just very quickly at the beginning. We've talked about derivatives. Let's talk about integrals. So integrals are also derived from limits, like derivatives are. And so they behave, again, very similarly to how we're used to from Calc 1. And it behaves very nicely for our purposes in here. So if you take the integral from a to b of r of t dt, so you have a vector function, that's going to be the integral from a to b of f of t dt I plus integral from a to b of g of t dt j plus integral from a to b of h of t dt k. So it turns out that integrals also can move inside the components of a vector function. So we can take them one at a time. And the note right below this, the fundamental theorem of calculus can also be extended to continuous vector functions. So if we take that integral, this is going to be equal to big R of t evaluated from a to b, where big R represents the antiderivative of little r. So it's a vector function whose integrals have already been taken. And then to evaluate that antiderivative, we take big R of b minus big R of a. So just like in Calc 1, integral from a to b of f of x dx, right, is big F of b minus big F of a. So you take antiderivatives and then evaluate. It's the same idea, just switched to vectors instead. So let's take a look at an example. So integrate, we've got 2 cosine ti plus sine tj plus 2 tk. So our integral of r of t dt, so that's going to be integral 2 cosine t dt I plus integral sine of t dt j plus integral of 2t dt k. So we get 2 sine of ti minus cosine of tj plus t squared k. And I know you might be wondering, wait a second, these are all indefinite integrals. Shouldn't we be adding like a plus c onto these? And technically, yes. But when we are dealing with vector functions like this, so this one would get its own plus c, this one would get its own, this one would get its own. What we like to do with vector functions is instead of giving each of these their own unique constant of integration, we go ahead and just take the I constant, the j constant, and the k constant, and we combine them into their own vector back here. So we have a plus c, where c is a vector, and again, this is the vector constant of integration. So the vector constant of integration, again, this would just be, like C1, C2, C3, something like that. It contains all of the constants from each component, I, j, and k. And we do that so we can kind of consolidate. Okay, it doesn't change anything about how we compute. Now, if this had been a definite integral, I want to look at just a little kind of follow-up here, follow-up example related to this one. What if we had the integral from 0 to pi over 2 of r of t dt? So what if it was a definite integral instead? Well, in that case, the antiderivatives are still the same. So we will still keep the same antiderivatives. And the I, J, and K should still be there because we're still just working with vectors in this case. We don't need the plus c for a definite integral. If you included it, it's not the end of the world. It's just that make sure that it subtracts away to 0 when you're done. But we are going to evaluate this from 0 to pi over 2. So for the pi over 2 case, we have 2 sine pi over 2 I minus cosine pi over 2 j plus this becomes pi squared over 4k minus 2 sine of 0 I minus cosine of 0 j plus 0k. And if we look at all the values we get out of these, sine of pi over 2 is 1 times 2 is 2. Cosine of pi over 2 is 0. Pi squared over 4 is what it is, so that's going to stay as is. Minus all these pieces. Sine of 0 is 0. Cosine of 0 is 1. And 0, of course, is just 0. So let's see what we got here. We have 2i and then 0j plus pi squared over 4k minus negative 1j, so plus j. So we end up with 2i plus j plus pi squared over 4k. So that would be the solution to the definite integral that corresponds to this indefinite integral. So we can solve both. And again, the main point of this section, kind of the punchline here, is that derivatives and integrals and limits all behave very similarly when it comes to calculating vector functions, as opposed to scalar functions that we've seen for our entire calculus experience. So a lot of good properties in here, a lot of things to take note of, but hopefully this is fairly intuitive as we move forward and continue using these and applying these to different properties in the upcoming sections. So that brings us to the end of section 13.2, and I will talk with you all very soon in the next one.